Hello and welcome to today's physics class. For this class, we'll look at the study of thermal expansivity in physics. For this topic here, there are two keywords there. The first one there is called thermal, while the other one is called the expansivity. What's thermal, or you call it thermal if you want to? Thermal has to do with heat, right? Heat has to do with thermal, right? So when it comes to thermal, we're talking about heat. And when it comes to expansivity, we're talking about the increase in length of an object. So I'm saying now that thermal expansivity is simply the increase in length of an object or a material due to application of heat. So when talking of thermal expansivity, just note that an heat is applied, right? So when a body or an object expand due to application of heat, hence it's said to be what the a thermal expansivity. When it comes to the study of thermal expansivity in physics, there are three concepts there. So there are three expansivity in physics. The first one there is called the linear expansivity, which is abbreviated as alpha. The second one there is called the area or superficial expansivity, which is represented as beta, while the last one there is called the cubic or volumetric or volume expansivity, which is represented with what? Gamma. We'll look at these three concepts one after the other. For this class, we'll look at just only linear expansivity. In our next two classes, we'll look at the concept of area and cubic expansivity. All right, we said when it comes to thermal expansivity, there are three concepts there. So we said the first one there is called the linear expansivity, represented as what? Alpha. So note that the first type of thermal expansivity is called linear expansivity, abbreviated as alpha. The second one there is called the area or superficial expansivity, which is represented as beta, right? While the third one there is called the volume, or you call it cubic expansivity, which is abbreviated as gamma. So this becomes the three kinds of expansivity we have. The first one is called the linear expansivity, which is represented by alpha, area or superficial expansivity beta, and volume or cubic or volumetric expansivity known as gamma. So let's look at the first one called the linear expansivity. Let's look at linear expansivity. All right, by definition, linear expansivity is simply the increase in length per unit length per degree rise in temperature. So when a material increases in its length and its temperature, it's said to be a what? A linear expansivity. So the increase in length per unit length per degree rise in temperature is said to be a linear expansivity. It's represented by a Greek symbol called alpha, right? So note that alpha is used to represent linear expansivity. Very important concept, please. So the Greek symbol for representing alpha, for representing linear expansivity, is called alpha. So mathematically, I'm saying that alpha, which is what? Linear expansivity, is equal to the increase in length length all over original length times increase in temperature. So this becomes your mathematical expression for linear expansivity, increase in length all over original length times increase in temperature. So I'm saying that linear expansivity alpha is equal to increases in length is simply change in length all over original length is L1 times increase in temperature that becomes change in T, right? So alpha is equal to change in length is simply L2 minus L1 all over L1 into change in T is T2 minus T1. So it becomes your mathematical expression for linear expansivity. All right, let's define something. What is L2? What's L1? What's T2? What's T1? What's change in L? What's change in T? So note that where L1 is simply the initial length, that's in meters. L2 is the final length in meters also. T2 is simply the final temperature in Kelvin, right? Also, T1 is the initial temperature, of course, also in Kelvin, right? So change in T is simply the what? Change in temperature, right? So in Kelvin, right? Also, change in L is simply change in length, of course, in meters. So note that L2 is initial length, L1 initial length, L2 final length, T2 final temperature, T1 initial temperature. Change in T is mean change in temperature, change in length means change in change in length means change in, so I have change in L means change in length. So I have this in front of you. At this point now, let's get the SI unit for um, linear expansivity. So we said that linear expansivity, of course, observe here, change in L, of course, that's in meters, all over change in L1 is also in meters, right, into change in T, that's Kelvin, all right. So if I cancel this, I'll have 1 over Kelvin. So at this point now, note that the SI unit, the SI unit, the SI unit, the SI unit for alpha is given as what? 1 over K or per Kelvin. So note that the SI is what? Per Kelvin. So note that the SI unit for alpha is simply per Kelvin, as you can see in front of you. So all right, with these few concepts here, let's look at some examples, some past questions on linear expansivity, and we're off. Welcome back. Example 1 says a copper rod whose length at 30 degrees Celsius is 10.0 meter is heated to 50 degrees Celsius. Full stop. Find its new length. Take linear expansivity, that is alpha, as being equal to 0.0000017 per Kelvin. So your first task there in science is to list out the givens. So that we given. So that we given from the questions there. Number one there. From the question number one says that a copper rod whose length at 30 degrees Celsius. So I'm given T1. That's the first temperature there. 30 degrees Celsius. Of course, this is in Celsius, and we said temperature is in Kelvin. So I'll convert this degrees Celsius to what? Kelvin. So by adding what? 273 to it, it becomes 30 plus 273. I'll have about 303 Kelvin. If I add these two, I'll have this. So the question says a copper rod whose length is 30 degrees Celsius is 10 meter, 10.0 meter. That's the length. That's number two there. I'm given L1. That's 10.0 meters. Of course, I'm not converting. So it's heated to 50 degrees Celsius. That's the second temperature. So number three there, I'm given T2 has been equal to what? 50 degrees Celsius. Of course, I'll convert this to Kelvin by adding what? 50 plus 273. This will give about 323 Kelvin. Of course. All right, I have this here. So take alpha number 4 there. I'm given alpha 0.000017 per Kelvin. So I'm given this. So find what? I'm going to find its new length. So of course I'm given L1. So it means that I'm looking for what? L2. That's the new length. So how do you get this done in science? So for this first, I'll recall my mathematical expression. All right, let's get this done, please. So my first task here is that I'll recall that we said that linear expansivity alpha is equal to what there? L2 minus L1 all over L1 into T2 minus T1. I have this. So note that I'm looking for L2. So I'll try to make L2 subject of the formula. What does it mean? There's an invisible one here. 1 times everything here we give L2 minus L1 to be equal to, multiply these two, I'll have L1 into T2 minus T1, then alpha. Combine 1, 2, and these 3 together, I'll have this. So I want to make L2 subject, so I'll take L1 here. So I have L2 to be equal to L1 into theta 2 minus theta 1, then alpha. Then if minus L1 becomes a plus L1. So at this point now, I can easily input my values here and get L2 as the new length. So my L2 now becomes L1. What's L1? That's 10 into T2 is 323 minus what's T1? T1 there is 303 multiplied by what's alpha? Alpha is this 0.000017. That's alpha. So plus what's L1? Of course, L1 is 10. So I have 10 here. So let's simplify this. What do I get? L2 is equal to 10 into, if I subtract 323 minus 303, I have about 20. This gives 20, right, into this alpha value. That's 0.00017, then plus 10. So I'll multiply 10 by 20. That's 10 by 20. That will give 200. So hence 200 multiplied by 0.0017 plus 10. All right, if I simplify this one, I'll have that L2 will be equal to 10.0034, sorry, 34. Of course in meters, because length, you said length is of course in meters. So of course my L2 becomes 10.003 4 meters. So these are to solve this particular problem. We'll look at still yet another example, right? And let's see what we get. Let's look at still yet another example to further understand the concept behind linear expansivity. One says a metal of length 15.01 meters is heated until its temperature rises by 60 degrees Celsius. If its new length is 15.05 meters, calculate its linear expansivity. All right, after this is done, first things first, I'll list out the given. So what am I given? Number one there, number one, very first thing I'm given from the question says that a meter of length, so I'm giving L1, L1 has been equal to 15.01 meters is heated until its temperature rises by 60 degrees Celsius. Please, when you the word temperature rises by 60 degrees Celsius, is that 60 degree? Is it its final temperature or initial temperature? Please take a bit and think. I'm hearing the word its temperature rises by 60 degrees Celsius. So I'm asking you now that 60 degrees Celsius, is it T2 or T1? That is that 60 final velocity or initial, sorry, is that 60 degree, is it final temperature or initial temperature? Think about it a little bit. Think about it. Of course, that 60 degree is not final temperature, and it's not an initial temperature. It's simply the change in temperature. So I'm given the change in temperature has been equal to what there? 60 degrees Celsius. So mind you, let me explain the concept. Let's say you're given T1 has been equal to what? 5 degrees Celsius. Given T2 as 10 degrees Celsius. So when the word the temperature rises. So let's say once the temperature rise by T1 and T2. So the question now is that once the temperature rises by T1 and T2, of course, is what? 5 degrees Celsius. So the temperature rises by what? 5 degrees Celsius. Are you there? So the temperature rises by 5 degrees Celsius. So it means that the way the way I got 5 degrees Celsius is that I did T2 minus T1. What's T2? 10 minus T1 is 5. Of course, this gives what? 5 degrees Celsius. So whenever you hear the word rise in temperature, is simply what? The change in T. And we said T2 minus T1 represents what? Change in T, right? From this concept here, from this one here. So I have this, right? So that becomes your idea behind ink rises by 6 degrees Celsius. So that becomes your original temperature change in T. All right. If its new length is that's L2, number 3 there, L2 has been equal to 15.05 meters. All right. Calculate its linear expansivity. So I'm looking for alpha is unknown. So how do I get this particular problem solved? The task is quite simple. I'll recall my formula. So recall that linear expansivity alpha is equal to L2 minus L1 all over L1 into change in temperature. Of course, alpha is equal to what's L2? L2 is 15.05 minus what's L1? That's 15.01 meters. So I have my L1 all over that same L1 is 15.01, right? Multiplied by changing T, that's 60 degrees Celsius. I'll convert this Celsius to Kelvin by adding 273 to it. So this give about 333 Kelvin. So I'll plug in the value here, 333 Kelvin. Yeah, 333. So if I subtract numerator, I'll have about alpha to be equal to 0.04. Subtract this 2, you have 0.04 all over, multiply the denominator, I'll have 499.833. From here now, alpha is now equal to divide numerator by denominator, I'll have 0.00012345. So 8 per Kelvin. So note that the S unit for linear expansivity is what? Per Kelvin, as we said earlier. So I have 0.000008 per Kelvin. So this becomes your answer to this particular problem. Next class, we'll look at the study of area slash superficial expansivity, right? So if you're interested in watching our full tutorial courses on JAM and Y classes, so I have a website. So visit my website, www.ganiarakri.com/courses. So I get a full-time access to these 100 videos for both JAM and YX students. So I have a full tutorial course for them. So visit my website. So you get a full life access to those courses and both physics, chemistry, and maths courses. All right, see you in our next class.